Today, we're focusing on what is, I think, the most fundamental paradox of the entire clean energy transition.
Okay.
We have basically won the race to make solar and wind generation incredibly cheap. I mean, in a lot of places, they are the lowest cost source of new power you can build, but they're unreliable. They're intermittent.
Exactly. And that's the whole ball game right there. The promise of green energy, it all hinges on this one massive structural problem. The sun and the wind, they just don't operate on our schedule.
Right.
We get this huge amount of power when the sun is high and the wind is fierce, which, leads to these times of surplus. But then
Yeah.
nothing. You get these long periods of total deficit when the grid is just begging for supply.
So the challenge, it's not really about generation anymore.
Yeah.
It's all about storage. We have to find a way to take that cheap surplus energy from the middle of the day and save it for when we actually need it.
Which is usually that evening peak.
Exactly, the evening peak.
And our mission in this deep dive is to examine a solution that is, well, it's almost deceptively simple, but it could be revolutionary. We're looking at a novel mechanical system that relies on one of the oldest, most reliable forces in the universe, gravity.
We're talking about gravity energy storage systems, or GESS. The basic idea is using massive movable blocks and potential energy to solve this huge reliability crisis.
And for this deep dive, we've pulled together, well, a pretty wide range of sources.
Oh, yeah. We've looked at everything from the deep technical reviews on system mechanics and performance metrics to corporate financial reports. We're going to dig into the Q3 2025 results of a major player in this space and articles detailing the actual commercial rollout and the economics of these systems around the world.
Okay, let's unpack this.
Yeah.
Because when you first tell someone that the future of the electric grid involves lifting 24-ton concrete blocks up and down a 175-meter tower, I mean, it sounds like something out of a classic sci-fi film.
It really does.
How can something based on such simple physics be the sophisticated answer to managing, a multi-trillion-dollar modern electric grid?
To really get the elegance of the gravity solution, I think we first have to fully internalize the problem, the economic and technical instability that renewables introduce to the grid.
It's not just that they're intermittent.
No, it's much more than that. The problem is how they create these extreme, incredibly rapid swings in what we call net load.
And that instability is perfectly captured by what has become, an absolutely infamous visual in the power industry, the duck curve.
The duck curve. If you're a listener who isn't familiar with it, you can literally picture a duck sitting on the water. It's a graph.
Right.
And this graph shows the real-time electricity demand minus the electricity being provided by solar over a single day. So around 8 a.m., grid demand is fairly high. That's the duck's tail as people start their day, turn on the lights,
But then the sun gets higher in the sky.
Exactly. And as the sun gets higher, massive amounts of solar energy just flood the grid. So the net load, the amount of power the grid thinks it needs, it just plummets. That deep curve in the middle of the day, that's the duck's belly.
And this midday glut of solar is a huge problem in itself.
Yeah.
It often creates a surplus, so much so that you get negative pricing in wholesale markets.
Which means they are literally paying people to take electricity off the grid.
And it forces even green generators to curtail, to just shut off because the grid simply can't absorb all that power. That is a massive economic inefficiency right there.
And then comes the real crisis point. The neck of the duck.
This is late afternoon, early evening.
Yes, and two things happen almost at the exact same time. Solar generation completely vanishes because the sun sets, and consumer demand surges. People get home from work, they turn on lights, start cooking, crank up the AC.
But that transition from that midday surplus to the evening peak is incredibly steep. It's almost a vertical wall of demand that a grid operator has to meet.
And historically, we've only had one reliable tool for that kind of rapid ramp-up.
Natural gas peaker plants.
Natural gas peaker plants. These are power stations designed specifically to spin up really fast and fill that gap. But they run on fossil fuels, they're expensive to operate, and they're the very thing we are trying to replace.
So if we want to get to a truly green grid, there's no way around it.
Right.
You have to eliminate those peaker plants. And the only way to do that is with storage. You have to capture the cheap solar energy from the duck's bellow.
And shift it directly into the duck's neck. It's the only way.
Exactly.
And our ability to make that transition smoothly is everything for what engineers call grid resiliency.
Right. Resiliency is the bedrock of the entire system. You have to maintain that core balance where the energy delivered must equal the energy consumed at all times. No exceptions.
And this brings us to a really crucial technical concept that gravity storage directly addresses the ramp rate.
Okay, that sounds like industry jargon, but it's incredibly important. It's basically the difference between a minor fluctuation and a citywide blackout.
It is extremely important. The ramp rate is just the speed at which energy delivery changes. Think of it in megawatts per second. If that rate of change is too abrupt, if solar drops off a cliff or demand surges too fast, the grid stabilizers can't keep up.
The analogy I always find helpful is you're driving a massive freight train.
Okay.
If you slam on the brakes or you jam the throttle to full, you risk derailing the entire system. You have to make those changes smoothly.
That's a spot-on analogy. And energy storage, especially a system that can inject or absorb power really fast, acts as that steady autonomous hand on the throttle. By smoothing out that ramp rate, storage keeps the grid stable.
So the need for storage, the imperative, is crystal clear. It's driven by the duck curve, by the need for resiliency. But if storage is the answer, why haven't our traditional options already solved this? Let's start with the big one, pumped hydroelectric storage, or PHES.
PHES is, it's the veteran of long-duration storage, or LDES. It accounts for something like 90% of all global grid storage capacity. And it works. You pump water up a hill, and you let it flow down when you need power.
Simple enough, but the limitations are, well, they're immense.
They're immense. And this creates the first big opening for something like GES. The sources are really clear on this. The biggest problem is topography.
You mean geography?
Exactly. PHES is severely restricted by its geographical and geological needs. You need two big reservoirs, a high one and a low one. You need a massive difference in elevation, and you need access to a huge amount of water.
Which means, what, 99% of the planet is just not suitable for a big PHES project?
Basically, yes. And even when you do find that perfect spot, it's often in a remote, environmentally sensitive area, which means you then have to build hundreds of miles of expensive transmission lines to get the power to the cities.
And good luck getting that permitted.
Precisely. The expense, the complexity, the environmental hurdles, it all leads to these huge project overruns that just scare away investors. The data shows this pretty clearly. In the U.S., for example, the last major PHES facility came online way back in 2012.
Over a decade ago.
So it's a proven technology, but we just can't build it where we need it or fast enough.
Okay, so if PHES is geographically stuck, we turn to the other major storage technology, lithium-ion batteries. Li-ion has been the darling of the transition, but it also has its limits, especially when you start talking about long-duration storage.
Yeah, we should define that. LDES, or long-duration energy storage, is really anything from, say, 8 hours of storage up to 100 hours or even more.
And lithium-ion is fantastic for short-duration needs, right?
It's the best. For things like frequency regulation, voltage control, maybe managing a 2 to 4 hour peak shift, it has an almost instantaneous response time. But as grid planners look at what it takes to survive, say, 3 straight days of cloud cover or no wind, they're realizing Li-ion is not the silver bullet for LDES.
So what are the main challenges holding back lithium-ion at that huge multi-day scale?
The source material really highlights 3 things: safety, supply chain, and durability.
Let's start with safety.
Okay, safety and siting. Lithium-ion systems have an inherent fire risk. It's a chemical system. And there's a risk of what's called thermal runaway. This makes building massive battery farms unattractive, or sometimes just impossible, in heavy industrial zones, inside mines, or on densely populated islands where fire safety is the #1 concern.
So you can't always put the battery where the power is needed most, like right next to a factory or a city.
It's a huge challenge. Second is the supply chain. The raw materials, lithium, nickel, cobalt, it's a finite supply chain with a lot of geopolitical complexity. Securing enough of that material for multi-gigawatt-hour deployments around the world is a serious scaling problem.
Especially compared to a system you can build out of local soil and cement.
We'll get to that. And the third issue is durability. Li-ion batteries degrade. They lose capacity over time with every charge cycle and just with age. A battery that gives you 100 megawatt hours today might only give you 80 in 10 years. And for a 100-hour system, you need enormous capacity, and you're going to have to replace those battery blocks every 10 to 15 years. That has a huge impact on the long-term economics.
So to recap, we have a storage mandate because of the duck curve. We have 2 established technologies. One is geographically constrained, that's pumped hydro. The other is constrained by safety and duration, that's Li-ion.
And that structural gap, that is the exact target for these mechanical gravity solutions.
This is where the beauty of simple mechanics really comes into play. As you said, GESS is basically trying to do what pumped hydro does: high capacity, long duration storage, but in a box.
A self-contained system,
Hmm.
no water, no chemicals. It's really pumped hydro without the water. It all relies on the very well understood physics of storing energy as gravitational potential energy.
Right, potential energies is just the stored energy an object has because of its position. If I lift a book off the floor, it has potential energy.
Exactly. So in a GS system, we're using that excess renewable power, the cheap electricity from the duck's belly, to do work. And that work is hoisting a massive object straight up against gravity. The higher it goes, the more potential energy it holds. That's the charging phase.
And so when the sun sets and the grid is screaming for power, you don't release water down a mountain. You just let that massive block descend in a very controlled way.
A very controlled automated descent. And as it comes down, it spins a motor that acts as a generator, converting that potential energy back into kinetic energy and then into electricity that flows back to the grid. That's the discharge phase.
And the scale here is what's so mind-boggling. These mobile masses have to be absolutely enormous to be useful for the grid.
The sources gave a really visceral description. These are not small bricks. They're custom-made composite blocks engineered to be roughly the size of a pickup truck.
And they weigh about 24 tons.
24 tons. Just to put that in perspective, a heavy-duty pickup truck might weigh 5 tons, so these are almost 5 times heavier.
And you need hundreds or even thousands of these, all moving inside a massive high-rise structure. You mentioned the Zhangyi project in China is 175 meters tall. That's what, like a 50-story building?
Roughly, yeah, 575 feet. And the whole system is just about lifting these 24-ton masses up that enormous height to store energy that would have otherwise just been wasted.
It sounds less like a power plant and more like a giant vertical automated warehouse, like an Amazon fulfillment center, but for concrete blocks.
That analogy is actually very, very relevant because the technology isn't one single invention. It's a synthesis. It pulls together proven tech from 4 completely different established industries.
Okay, what are they?
First, you have the mechanical systems of cranes and elevators, which are designed for high-precision, heavy-duty vertical movement. Second, you have the logistics and safety standards from the shipping and port industry, which is all about managing massive cargo safely.
I see. And third
is the highly efficient bidirectional motor generator technology. That's the piece that allows the same machine to use electricity to lift the blocks and then generate electricity when they're lowered. Think of it like regenerative braking in an electric car, but on a colossal scale.
And the fourth pillar is material science, right?
Right.
The actual stuff the blocks are made of.
Exactly. Which, as we'll get into, allows them to be made from waste materials. But the key takeaway here is that none of the core components are really new. It's a brilliant recombination of proven, low-risk, decades-old mechanical systems.
All of which is overseen by some very sophisticated proprietary software.
Yes. The software, which is called VaultOS, is the brain that orchestrates this entire complex ballet of concrete blocks.
So what is this machine vision software doing that a person couldn't just do with a joystick?
Well, it's optimizing the whole process in real time. It's looking at grid signals, weather forecasts, wholesale market prices, and it's autonomously deciding when to charge and when to discharge to maximize value. It's also choreographing the movement of hundreds of individual blocks, managing the precise descent rate for each one to meet the grid's exact megawatt output requirement second by second.
You just can't do that manually.
Not at the speed and precision required.
How fast are we talking? If the grid suddenly needs a jolt of power, can these things respond quickly enough to help with that steep ramp rate on the duck curve?
Absolutely. The technical analysis we reviewed shows these systems can go from idle to delivering a steady state of full power in just 40 to 80 seconds.
Okay, that's significantly faster than firing up a traditional gas turbine peaker plant.
Much faster, which makes them incredibly valuable for maintaining grid frequency and stability when, say, a cloud passes over a giant solar farm and its output suddenly drops.
So let's track the evolution of this a little bit. Yeah. The sources note there were a couple of distinct generations that led to where we are now. It started in Switzerland, right?
Yes, in Lugano, Switzerland. That was the Commercial Demonstration Unit, the CDU, which hit mechanical completion back in July 2020. That used the original EV1 design.
And what did that look like?
The EV1 was a single, very tall tower with a big central crane mechanism, and that crane would stack and unstack these blocks around the perimeter of the tower.
It was the proof of concept. It showed that the physics worked, the software could control it, but it wasn't really built for mass production.
Exactly. It wasn't scalable or modular enough for global commercial deployment, So the focus pretty quickly shifted to the current commercial platform, the EVX system, which was introduced in 2021.
And that uses a different design, a fixed structure and a trolley setup.
Yes, and that structural change is everything for commercial success. It's all about modularity.
So instead of a custom-built one-off tower for every single project,
Right. The EVX platform allows the system to be scaled up or down. You can adapt it to different site sizes, different power needs. You can start with a small 40 megawatt hour system and scale all the way up to these multi-gigawatt hour facilities they call energy vault resiliency centers.
so that modularity, the ability to build with standardized blocks, it lowers construction risk and it lowers cost.
Mm.
It lets them move out of the lab and into the real world as industrial scale infrastructure.
And that combination reliable mechanics plus flexible, scalable construction is how they solve the deployment problem that just plagues pumped hydro, which brings us to the key advantages GESS has over the competition.
When a utility planner is looking at new storage, what are they balancing?
They're balancing three big things: cost, performance, duration, and maybe most importantly, flexibility of placement. And GESS scores really well on those last two.
So let's start with that placement flexibility or siteability. You called it the biggest market differentiator. If pumped hydro is stuck in the mountains, GESS is basically storage for everyone else.
That's a great way to put it. It's storage for the flatlands and the brownfields. GESS systems are free from those geological constraints. You can put them almost anywhere you need electricity storage.
Like in existing industrial parts or near cities.
Exactly. Or, and this is strategically very important, on the site of a retiring fossil fuel generation plant.
Why is that such a big deal? Why build on the site of an old coal plant?
It's all about infrastructure efficiency. Those old coal and gas plants were built for a reason. They're located near major population centers or big industrial loads, and critically, they already have existing high-capacity connections to the transmission grid.
The expensive power lines are already there.
The hugely expensive grid interconnects are already there. So by building a non-chemical, safety-compliant gravity storage system on that same plot of land, you get to reuse all that existing grid infrastructure. You avoid the decade-long wait and billion-dollar cost of building new transmission lines from some remote location.
Which means you can get long-duration storage onto the grid much, much faster.
And this flexibility makes GSS useful across the whole spectrum of needs, from that 4 to 10-hour daily peak shifting for the duck curve, all the way up to the 8 to 100-plus hour requirements you need for true grid resilience against, a week of bad weather.
And the nature of the storage itself, concrete blocks versus chemical cells, that solves another huge market hurdle, which is safety.
The non-chemical nature is a massive selling point. GESS is purely mechanical. There is no thermal risk, no off-gassing, and no fire risk like you have with lithium-ion.
Which opens up markets where batteries are a tough sell.
Entirely new markets. If you're running a mine, a heavy industrial facility, or an island grid where land is scarce and fire safety is paramount, gravity systems solve that concern completely.
And beyond the safety, there's the lifespan of the asset. Mechanical things, tend to last longer than chemical things.
And that is the key to the whole economic argument. The EVC design is stated to have a 30 to 50-year design life, maybe even longer, and it has little to no degradation in capacity over those decades. A GES system that can provide 100 megawatt hours today will still provide 100 megawatt hours in 30 years.
Whereas a battery won't.
Right. A battery will have degraded significantly by then. So when you calculate the levelized cost of energy, the LCOE, which is the total cost of the system over its entire life, the durability of GESS really tilts the math in its favor for those long-duration applications.
Okay, so this is where it gets really fascinating. The part that connects environmental cleanup directly to clean energy storage, the circular economy link. These blocks can be made of waste.
This is the surprising double environmental benefit. The composite blocks are designed to be made primarily from low-cost, locally sourced, and upcycled materials. You don't need a global mineral supply chain. You just need local waste streams.
What kind of waste streams are we talking about here? This is pretty incredible.
Yeah. The sources list things like local soil, which is obviously abundant, mine tailings, which are the waste byproducts from mining operations, even shredded, decommissioned wind turbine blades.
Wow.
But the most compelling input, environmentally speaking, is coal combustion residuals, CCR. That's the technical term for coal ash.
Coal ash, the stuff left over from burning coal for electricity. That is one of the largest and most toxic industrial waste streams on the planet.
It's a massive environmental liability. It contains heavy metals. It's known for leaching contaminants into groundwater from these unlined disposal ponds. There are literally billions of tons of it stored around the world.
And this technology can just use it.
It can use it. By integrating this coal ash into the GESS blocks, the system does two amazing things at once. First, it accelerates the transition to renewable energy storage. Second, and this is critical, it permanently and inertly binds that toxic coal ash into a stable structural composite block. It locks it up and prevents it from ever contaminating the environment.
So you're taking the toxic legacy of the fossil fuel era and literally turning it into the infrastructure for the green energy future.
Yes. The material isn't just cheap, it solves a massive remediation problem at the same time. It completely redefines the economics of environmental responsibility for these utility companies.
It's a way to profit by cleaning up your own mess.
It's a profound model. It's incredibly attractive to utilities and governments that are under huge regulatory pressure to clean up these coal ash ponds.
Okay, so GESS overcomes the geological problem of pumped hydro. It overcomes the safety and duration issues of lie-on, and it provides a sustainable waste-utilizing input for its core component. That seems like a perfect setup for commercial success.
Well, the transition from a brilliant concept to, bankable infrastructure, it all comes down to successful large-scale deployment. The big question for investors and for grid planners is, does this mechanical marvel actually work reliably at utility scale?
And the answer, increasingly, is yes, based on the real-world deployment we're seeing, especially in China. Let's start with the first commercial facility to come online.
That would be the Rudong EVX facility in China. It's a 25 megawatt, 100 megawatt hour commercial system. And crucially, it's successfully completed all of its testing and commissioning by May of 2024.
So it's officially up and running.
It's up and running, and that operational success provided the empirical validation that the market needed. It proved the mechanics work, the software works, and the grid integration works.
And the second major project shows the sheer physical scale this tech can reach.
That is the Zhangji City GESS in China's Gansu province. Construction on that started in April 2023. This is that 175-meter structure we talked about earlier. It's designed for 17 megawatts of peak output and 68 megawatt hours of capacity, so it can provide sustained power for 4 hours or more to that regional grid.
In both of these projects, Rudong and Zhangji, they received a pretty significant stamp of approval from the Chinese government, didn't they?
They did. They were selected by China's National Energy Administration as new energy storage pilot demonstration projects. That's a signal. It says that GESS is seen not just as a novelty, but as a critical strategic piece of the puzzle for managing grid congestion and helping China meet its very ambitious national dual carbon goals.
So the validation is strategic, not just technical.
Exactly.
Okay, let's pivot from project validation to financial stability. The company behind this is making a really big shift in its business model. They're moving from just selling projects to actually owning the infrastructure themselves. This is where the business story gets really interesting.
This is a crucial evolution for any infrastructure company. They're moving away from the traditional EPC model, that's engineering, procurement, and construction, and they're moving aggressively toward being an asset owner and operator, which they've formalized through their Asset Vault platform.
Let's unpack that difference, because it really dictates how investors value the company.
Right.
What's the problem with the old EPC model?
The EPC model is project-based. You sell a complex infrastructure project, you build it, and then you walk away with a one-time lump sum payment. That revenue is, well, it's often volatile, it's lumpy, it depends on construction timelines, and it usually has lower margins because of all the risk involved. Investors tend to see those companies as speculative developers.
But the Asset Vault model provides the exact opposite. It's about predictable, recurring, high-margin revenue, the kind of thing that infrastructure investors really value.
Exactly. When you own the asset, you capture multiple, highly predictable revenue streams for decades.
Okay, what are they?
First, you get high-margin revenue from long-term service agreements, or LTSAs. That covers all the operations and maintenance for the asset's 30 or 50-year life. Second, you get licensing fees for the software for VaultAway, which scales incredibly well. And third, and this is a big one, you can do energy arbitrage.
Buy low, sell high.
Buy low, sell high. You use your own asset to charge when power is cheap in the middle of the day, and then you sell that power back to the grid when it's expensive during the evening peak. You capture that spread.
So this shift, It changes the entire risk profile of the company. It moves it from a speculative developer to a reliable infrastructure platform with multi-decade cash flows. And that context is absolutely critical for understanding the surprising financial results from Q3 2025.
This is where the narrative completely flips. It shows what the market really cares about. The company reported a pretty significant loss per share, -10 cents, which missed the forecast of -4 cents.
That's a big miss.
And revenue came in at $33.3 million when the forecast was for almost $49 million. So they missed on the top and bottom line. By any traditional metric, this should have sent the stock tumbling.
And yet the stock actually rose. It was up 3.2% in after-hours trading despite the huge miss. What are investors seeing that the headline numbers are hiding?
The market is looking right past the short-term lumpiness of that old EPC business. They're focusing entirely on the long-term strategic execution of the asset vault model. And there were several data points in that same report that validated the strategy.
Okay, so what were the signs of long-term health that overshadowed the bad quarterly numbers?
First, while revenue missed the forecast, it still represented a massive 27-fold increase year over year. The growth trajectory is just undeniable. Second, their operational efficiency got a lot better. Their adjusted EBITDA loss narrowed sharply from almost $15 million a year ago down to just $6 million.
So they're growing like crazy and getting more efficient at the same time.
Exactly. And most importantly, investors saw real, tangible proof of the expansion of the asset vault portfolio. That's the long-term, high-margin revenue generator. They're out there acquiring and developing major storage sites in key global markets.
The sources mention specific deals in Texas and Australia.
Yes. They acquired a 150-megawatt interconnect site near Houston, Texas. That's one of the fastest-growing power markets in the world. And even more compelling, they acquired a 125-megawatt site in Australia called Stony Creek.
And what was special about that one?
That site came with a definitive 14-year long-term energy service contract already signed and secured with the New South Wales government.
A 14-year government contract. That is the very definition of predictable, high-margin revenue. So these acquisitions are physical proof that the asset vault strategy is working.
That's what the market saw. Those first few asset vault projects alone are expected to contribute about $40 million in recurring annual EBITDA as they come online. That is the kind of cash flow that infrastructure investors love.
So let's position GESS in the broader competitive landscape. Who are its main rivals and what's its specific niche?
GESS is competing directly in that long-duration energy storage space. So its rivals include things like advanced flow batteries, which also target durability and safety, thermal storage solutions, and for really, really long duration like seasonal storage green hydrogen.
But the math, as you said, it all comes down to the total cost per usable kilowatt hour over that 30 to 50-year life of the asset.
It absolutely does. And GES really starts to shine when the need is for 8 to 100 plus hours of sustained power. That's the zone where the cost of replacement and the degradation of lay-on becomes prohibitive. The commercial wins are happening in geographies where batteries are constrained by fire risk and in industrial sectors that just need multi-decade reliability without any capacity fade.
So it's positioning itself as the indispensable, non-chemical, siteable, high-durability option.
The option you need for a truly resilient green grid.
This has been an incredibly thorough deep dive. We started with this basic paradox. Cheap, clean energy is basically useless if it's not reliable.
And gravity energy storage provides this elegant, almost surprisingly simple mechanical answer. By just leveraging the basic physics of lifting heavy blocks, GESS stores potential energy in a way that overcomes the big problems of its predecessors.
It overcomes the geographical constraints of pumped hydro.
And the safety and duration constraints of lithium-ion batteries.
And, maybe most profoundly, it ties the energy transition directly to environmental remediation. It uses waste streams like coal ash to build the very infrastructure that stores our clean energy.
So what does this all mean for the future of our power grid?
That's the big question.
I think it means the era of the single, one-size-fits-all storage solution is over. Grid reliability in a green future is going to rest entirely on diversifying the storage mix.
Right.
We have to move beyond just lithium-ion and embrace these non-chemical, high-durability, siteable mechanical storage systems like GESS. They address the toughest structural challenges utilities are facing: long-term capacity degradation, safety, and supply chain constraints. And the commercial success we're seeing proves this isn't theoretical anymore. It's happening right now.
And that structural change, that diversification, it opens the door to entirely new possibilities. especially in sectors where power demand is just exploding, like the digital economy.
Absolutely. Think about the massive power requirements of AI, of these giant data centers. These systems need continuous, high-density, absolutely uninterrupted power. 247 reliability is non-negotiable for the digital backbone of our world.
And that's our final provocative thought for you to consider.
Yeah, the ability to site large-scale, non-flammable, and citable long-duration gravity storage right next to these massive energy-hungry digital infrastructure loads that could redefine the geography and reliability of the entire digital backbone. It's how we can support the growing demand for computation without having to rely on a constant feed from polluting power plants. That is the next great power challenge this foundational technology is uniquely positioned to solve.